And there we go.
There
All
you
right.
go.
Well, welcome everybody to the OWASP Moncton chapter meetup. We had the last one was back in December, so we had a nice little 3 months off. Just the new year, COVID work, and everything else basically made it so that we waited 3 months. I hope the next one's not going to be another 3 months, but hey, if it is, it is. All right, Brian, if you want to go to the next slide. So just to give a really quick introduction to what the OWASP Foundation is, it's mostly around the security of software. And what they do is they do projects, they do a bunch of chapters like this one all across the world, thousands of members, and they do conferences and all kinds of stuff like that. The Moncton OWASP chapter, our goal, and we'll talk about this in a few slides. Basically, we're here to support OWASP, but our main focus is just to get people together, like-minded people together, so we can talk security, learn stuff, and get the chance to basically participate in the community. So it's always fun. Go ahead, Brian. So I'm just going to do a little bit of housekeeping here. We had a change of leadership at the OWASP Moncton chapter. It's really young, so of course things are going to change. And Jason Sheehan has basically decided to take over the co-leader position from Tony English. And I'm really happy to have Jason with us. He's helped out a lot with this presentation, and I'm sure he'll be helping out a lot in the future. So Jason, if you want to introduce yourself, you'll probably do a better job than myself.
No, that was great, Julian. We can actually skip this. No, it's all right. Yeah, currently working as a cybersecurity analyst at Organigram. It's actually a new position I just moved into this week. Couple certs, nothing too groundbreaking. Currently enrolled in the PWK, which I'm super stoked to go on that journey and hopefully see the OSCP at the end of the road and get that accomplishment. Believe it or not, that picture that you're seeing, that's not me. That's actually my little doggo. But don't let the face fool you. He is a little diva, but he's still a good doggo.
Awesome, thank you, Jason. Again, quick about me. I work at Mariner. I've got a few certs. I actually just passed my CRISC. It's not on here because it's not official, because they haven't told me it was official yet, but just passed it last week. Do a bit of volunteering, including OWASP, Canadian Ski Patrol. I've worked with the EC Council a little bit to set up the new CEH exam. I'm an outdoor enthusiast. I'm a father to 2 humans, 2 cats, and 1 dog. So if ever I'm walking down the street, you see me, you wave at me, and I completely ignore you and I mumble, it's because I haven't slept for the last 2 days. All right. So what I spoke about this a little bit earlier, but again, we want to share knowledge. It provides a place for us geek types to have conversations. Share career information is always good in the OWASP group in LinkedIn. If ever you have any information you want to share, whether you're looking for work or you're looking to hire people, it's a good place because a lot of cybersecurity people will be in there. I think the group is almost to 100 now. And we want to grow security in our part of the world where, as a consultant, I go into a lot of businesses and I see in the last 3 years, I've seen a lot of growth in cybersecurity, a lot of really technical people that are getting hired, and board of directors and the executives are really starting to pay attention. Unfortunately, it's because of all these breaches that we've been having across the world, but hey, whatever brings their attention to a growing problem, it's great. So our goals, we want to do more presentations, more webinars. Anybody that has topics they'd like to hear, feel free to reach out. Jason and I will be putting out a call for speakers. So if anybody has anything really cool to talk about and expertise that they want to share, it would be awesome for you guys to reach out. And Evan's going to talk about a project that he has too, which kind of flows into this. And so we're going to support each other and possibly even merge at some point. But anyways, we'd like to have a local conference eventually. Local can be anywhere between St. John, Fredericton, and Moncton. could be virtual. Everybody's kind of, I was at a virtual conference about 2 weeks ago, and I don't know, it's not the same. You have to pay attention. It's not as good. So I'd rather not. And it would be pretty awesome to have sponsors eventually. Again, when it's virtual, we don't need money, but if ever we meet in people, it's cool to have drinks, well, coffee, not, and and food and whatnot. So it would be great to have sponsors eventually. So semi-open mic. Evans, if you want to talk about your little project and introduce yourself, that'd be awesome.
Yeah, for sure. Hey, I'm Evans. I'm a cybersecurity grunt, like I'm assuming a lot of people here. And I'm just putting together a little group, a lot less formal than the OWASP stuff, basically to try and do 20-minute presentations every couple of months, mostly as a practice venue for people looking to do more formal things. So, like if you have some content you're working on, go there, try it out, see what your peers say, stuff like that. So if anyone has any interest on speaking or attending or any questions, I'll put my email address in the chat. Feel free to drop me a line about it.
Perfect. Thanks, Evan.
Awesome.
I find that that's a really cool project. I like it. And Ben, if you wanted to talk a little bit about what you're up to these days.
Yeah, hi, I'm Ben McCarthy. This is my first time actually joining OWASP here in Moncton. Julian and I talked about it a while back. I actually use OWASP as part of our cybersecurity curriculum at MBCC. We have I teach in the cybersecurity program there, and we have a module on software security mixed in with network security and pen testing and blue team type activities. So I was very excited to join. One of the main reasons I've missed a lot of the past stuff is on Tuesday nights, I'm part of another group called Civic Tech. I don't know if people have heard of Civic Tech, but they're basically chapters pretty much in most of the major cities across Canada. They're kind of affiliated with Code for Canada a little bit. We get some guidance and help from them and on national kind of initiatives. But we have a chapter in St. John, and basically the concept, in a nutshell, is technology for social good. So we try to bring together community groups and nonprofits and that have issues that they're trying to solve, and we try to bring the technology folks together with them to actually work on projects and solve issues. An example from the Fredericton group, there's a group in Fredericton here in Brunswick and in St. John. The Fredericton group created the River Watch app for watching for floods along the river and things like that. So anything like that where we can step in with open data and solve a community problem. It's kind of a fun group, very open, very inclusive. You come when you want. In St. John, we meet every Tuesday night at 6:30. And it's kind of a forum like this. People can pitch new ideas. They can listen to what other people are working on, join a team, leave a team, jump in and out. It's very informal that way. But it's been going on for about a year, and it's quite fun. Very applicable to the Moncton region is there's a few people in Moncton that have contacted us to see about opening up a Moncton chapter. And Evan, your stuff about doing 20-minute tech talks and things like that, Civic Tech is actually completely open. So some people will come and pitch, hey, I want to do this online course. Does anybody want to do it with me? And they'll get together and work on a course together, or even a book club even. So the concept of technical discussions in areas around cybersecurity or any other technology field, you could come and just say, hey, does anybody want to listen to this presentation? And then go off into a breakout meeting and have that little side chat at any given time. So it's kind of neat. So it's pretty open in all those ways. So if anyone's interested, I'll drop my email into the side chat here, and we can sync up. But yeah, coming soon to Moncton.
Awesome. That's awesome. It's good to see there all these initiatives taking place. I don't know if people are just at home bored with COVID and all these ideas are flowing, but I love it. It's great because we used to have cyber socials in Moncton, and that kind of went away pretty fast, and there was nothing, just nothing. Perfect. All right, Brian, next slide. All right, so we're going to talk about current security events. One thing I just want to bring up is that Glenn E. Clark from Halifax, he has a training center that he runs. He wrote a book on Pentest Plus, and we are going to be raffling off that book. One thing that we need to do is we can't. He's going to be shipping that book out of pocket, so I don't want him to send it outside of Canada. So if anybody here is not in Canada, please just drop me a message or anything like that. We'll be taking names and doing we'll be doing a draw after Brian's presentation. Yep. Okay, thank you, Keani. All right, so Jason, go ahead if you want to talk about security events. I don't know what this Microsoft Exchange hack thing is. I've never heard of that.
It's it's honestly nothing. Let's just jump over it. Yeah, this is oh man, this is just so bad. It started with 4 0 days that have been just being exploited. I think they're called Hafnium, the Hafnium nation state group, or a group out of China, I think it is. The last time I checked, they said that there's at least 30,000 U.S. organizations that were hacked from this, and it's just going to grow. Now, Brian Krebs, actually on his website, he has an article that was posted yesterday or the day before, and it's kind of like a rough timeline of the whole process from when the vulnerabilities were reported, when it got to Microsoft, when they escalated, and when the attacks started happening. Very cool to check. Well, I mean, not cool as in, hey, it's cool it's happening, but it's cool to see the timeline of how everything plays out. I think the biggest worry is the last time we've seen such a massive exploit that just keeps growing and growing and growing was the Eternal Blue, and then that eventually grew into WannaCry, and then it just massive damage worldwide. So if you have an on-prem Exchange server, please patch it. To do what you need to do. This is pretty bad and scary stuff.
And you need to do an assume breach scenario.
Yes.
If you have an Exchange server that's exploitable in the wild, you have to assume you've been breached and basically go through the full incident response process.
Right. Yeah. So speaking of scary stuff, the Florida water system compromise or hack. Essentially, hackers got in and they made a change to the chemical composition of the water. So like in an attempt to poison it, it was caught, thank goodness, but they got in through TeamViewer. And then it was also released that the organization there in Florida, it was also on a Windows 7 system. So you have a combination of a few things, right? You have out-of-date software, TeamViewer, end-of-life operating system, but it also draws big attention to the importance of IoT and OT security, which is so many things are process control right now, and the amount of non-secure ones out there should be eye-opening, and I think more focus should be on that. A little bit of a balance here with some kind of feel-good stories here. So the NetWalker ransomware. This was one of those crime syndicates. Anyways, it's starting to be disrupted. So there's authorities out of Bulgaria, I think it was. They started disabling like certain resources relating to NetWalker. There's actually a guy in Canada. I think he was out of Gatineau, Quebec, I think. Yeah, he got arrested for involvement, and I think he made it was something silly, or something like $20 million or $25 million off of NetWalker. But it's good to see, like you hear all these stories about ransomware and how it just keeps evolving and evolving. But the fact that the authorities can go out and shut these things down, or start poking holes in it, and kind of say there might be some further investigations going along to these other ransomware families or crime syndicates. I know it's unfortunately never going away, but it's nice to see the good guys get the wins and whatnot. Joker Stash, that was another interesting one. It was referred to as the largest underground shop for like selling credit card data on the dark web. At the end of February, they announced that they were shutting down, and this was a couple weeks after that the United States and Interpol seized a number of their servers. And these servers were touted as, you know, and I'm using my air quotes here, untouchable or, you know, bulletproof servers. Like, so it goes to show that even, hey, you know, these cyber criminals, while they might believe that they're untouchable, you know, the authorities will still find a way. And I can't even imagine the amount of people that were affected and probably had their lives altered because their stuff was for sale on this forum. So yeah, nice to like I said, see the good guys get some wins here.
Perfect. Awesome. So we're going to spin through this next slide fairly quickly and give Brian time to do his presentation. We don't want to go a bit over, but yeah, go ahead, Jason.
Yeah, so this is just some quick fun edition security events. We recently competed in the Tenable CTF. I was lucky enough to compete with Julian, Brian, and Naomi on their team. My first CTF, super fun. I could spend, you know, the next 40 minutes talking about how much fun I had, but I won't. There's another CTF coming up this weekend, NahamCon. It's put on by John Hammond, who puts out great stuff. Recommend anyone to check it out who's interested. Try HackMe, the learning platform for hacking, pen testing, whatnot. They also release networks, which is different from their standalone boxes. So Wreath is going to be their next one. Throwback was their previous one, which was super fun. So assuming this one will be fun too. And Julian, I guess if you want to speak to PancakeCon.
Sure, PancakeCon. It was a pop-up conference last year, and it's so cool. Basically, the talks are focused 20 minutes on something cybersecurity that is focused towards students and beginners. And the last 20 minutes of the talk, every talk is 45 minutes. The second half of the talk has to be the subject needs to be something that is not cybersecurity related whatsoever. I think there's one, it's something like breach credentials in bourbon, and like just some cool talks. And basically I applied for, I responded to the call for speaker, and they accepted me on one of the talks. I'll be talking about hacking and climbing. And I've had that idea in my head for about a year that I wanted to find a way to merge the two together, and I don't need to merge them because I can just talk about hacking and then I can talk about climbing. So it should be fun. It's coming up on March 21st, based out of Chicago, I think they are. Check it out if you get a chance. Should be interesting.
Will you be able to provide a link in the video chat here?
Absolutely. And what I do is after this, what I'll do, on the website, I'll put a link on LinkedIn to our website, and you'll have all the links and everything else, all the stuff that we've talked about here. But yeah, I'll send the link here. All right. Sweet. So I think Brian, we're 20 minutes in. It's about time to get started. I'm going to hand it off to Brian. Brian's, I think you have a presentation slide there.
I do.
Perfect.
Y'all see it, right?
Yeah. So Brian is, I'm happy that he accepted to give us an introduction to Vote for Overflows. Brian's a coworker. He's also a friend. We've done stuff outside of work, like CTFs and whatnot. So go ahead, Brian. And
sweet,
guys.
All right.
Sure, you'll do.
Yeah. So I'll take it from here, Julian. So the moment everyone has been waiting for, the presentation on the technical topic. So I call this an introduction to buffer overflows. A buffer overflow is basically when a specialized hacking technique. I think it was like pretty well known. I think they've been pretty popular. And I'll get more into the history of that later. But yeah, my name is Brian Yip, and this is going to be an AppSec presentation. And some of you guys know me from Online Presence as Rocket. That's my my user alias. So let's dig deep into this fun topic. So I currently, like Julian said, I'm a coworker with him. So I mostly specialize in penetration testing. That's mostly on enterprise networks and software applications. I am OSCP certified. I got my certification back in October 2020. It was definitely an adventure. And for anyone who's interested in pursuing the offensive side of security, I can highly recommend it. Again, CTF player, participated in Tenable CTF, Julian, Jason, and Naomi. That was great. We did fantastic there, and I hope to see more of that in the future. I'm also an InfoSec live streamer, so this is not the first talk I do. I have a whole YouTube channel and a blog of kind of like live demos and presentations like this one that you're going to see today here on OWASP Moncton. And if you take a look at my room, you probably see an electric guitar back in the right hand corner, and that's because I play music. I also produce music. So I used to be quite into the hard rock and heavy metal scene, but now I've transitioned more into like electronic music, more like dubstep and drum and bass. And last but not least, adventuring. Who doesn't like adventuring, exploring the world, right? So back in the day, just to give some more context on where this talk is coming from. I used to be a systems software engineer. So when we talk about buffer overflows, you're going pretty low level into the technical details, and you're usually working with programming languages and platforms like C and C++. So back in the day, I used to develop real-time software systems, more specifically on implementing network protocols. So we can there were like quite a bunch of bugs there that I eventually saw as I transitioned into my InfoSec analyst career at the same company. So the software that me and the rest of the team wrote, we eventually started finding security bugs and writing exploits for them. And eventually that kind of got a bit stale because I was always looking at the same thing over and over again. And eventually I said, hey, I need to change my career path and do pen testing and look at the bigger picture. And that's where I started on my journey for OSCP, which I achieved in October 2020. The links below are my YouTube channel and my blog. So if you enjoyed this talk, be sure to check those two out. All right. Like I was talking about history, buffer overflows, they're one of the biggest types of hacks in history. And they've been around since the 1970s, which was before probably most of us were even born. But it wasn't until that we saw the Morris worm from 1998 where buffer overflows became a real big issue. That's because the Morris worm, written by yours truly, Robert Morris, he exploited the finger D service and through a buffer overflow and was able to propagate that worm to adjacent computers on the internet and spread his software throughout the world that way, infecting tons of computers. Now, this hacking technique was pretty obscure, but it was eventually this sort of attack got better documented in 1996 on Frack magazine. Most notably, the article was called "Smashing the Stack for Fun and Profit," written by Aleph One. I was also introduced to that back in university when I was learning about, I guess I would say buffer overflows. It was actually a course on computer architecture, but I don't recommend reading that. It's very dense. Don't smash your brain on that. There are way better resources nowadays, like Hacking, the Art of Exploitation, and even this live stream. And I'm bringing up Hacking, the Art of Exploitation, this book here, because this is what got me into InfoSec. I was like, how do people hack your computers? I don't want to get hacked. So I picked up a copy of this book back in 2014 and started reading it. I didn't understand what was going on at all. It was very complicated. I think I read it like 3 times, but eventually it clicked. And after reading it 3 times and I try running these hacks on a modern system, I was like, oh, it feels bad because none of my hacks worked. Because when you're learning this stuff, it's usually in a vulnerable environment, which is exactly what John Erickson provides you with to practice this stuff, but it's also very important when you're starting out. And throughout this presentation, we're going to be witnessing some buffer overflows on an environment that I made non-secure because I didn't want to download a VM, but we'll take a look at that later. Moving forward to modern days, I'm pretty sure lots of you are familiar with The Legend of Zelda Twilight Princess on the Wii. There's actually a buffer overflow in that game where you could overwrite the name of your horse to a really long buffer and then eventually trick the program's execution to invoke arbitrary shellcode. And you can just think of shellcode as really low-level computer instructions. Basically, you can execute any computer program on the Wii in that sense. And then if you might ask yourself, are buffer overflows still happening or relevant in 2021? Well, yes, they are. If you go and click this link right here or look on cv.miter.org, you're going to find buffer overflows happening in tons of software. And one that really stood out to me was CV 2021-21156, which is dated as February 2021. And that was a heap buffer overflow in Chromium's V8 JavaScript engine. And just to be clear, Chromium is basically non-commercial Google Chrome. It's still developed by people at Google. And yeah, you're able to execute a malicious JavaScript, and then boom, you suddenly have a heap buffer overflow in the JavaScript engine, which is mind blowing. Okay, so if I were to tell you what this was in English, what is a buffer overflow? To me, it's just a software attack where overflowing one region of memory goes into an adjacent memory region. So if that's a bit of a mind twist, how about we take a little bit of a visualization right here? So let's assume we have a little C program right here, and we have a buffer of 64 characters in it. And I'm just typing hi in here, terminated with some null bytes. So a null byte is represented by hex 0. And then we have an adjacent memory region here. It's called target. And target is what we want to overflow. And in this case, I'm being very clear. I'm saying a target is a uint32t. So you have basically you have 4 bytes or 32 bits, and we just want to overwrite this memory space right here. So let's go flood this with 64 A's and dead beef in the target. So we're suddenly taking control over what this variable is by overflowing this buffer right here. And if you're conducting these sort of attacks, you might ask yourself, well, what do I even bother overflowing? Well, if you're a security researcher, for example, or a software engineer, you're trying to defend your programs or attack them, function pointers would be a really good variables to overwrite, because in programming, a function pointer is something that you can call and invoke to redirect program code execution. And that also ties to return addresses as well. So whenever you call a function and you return from it, you're returning back to the function that called you. But if you trick the program into saying, hey, this evil function called me instead, now you suddenly redirected flow execution by overwriting that return address. And additionally, you can go ahead and, like I said, overflow adjacent memory structures. And that may be abused to bypass certain security measures or even enhance your usability of the app in certain cases. But the reason why you should care about these is because it doesn't take a genius to crash a program through a buffer overflow. And some of the most common vulnerabilities you'll find associated with buffer overflow attacks are denial of service. And that's because, as we'll see throughout this presentation, there are a lot of countermeasures that have been introduced that make the exploitation of such attacks very difficult. But crashing an app, that's simple. You just have to throw a lot of garbage at it, and boom, you've crashed the app. Again, you can alter the program flow execution in expected ways by changing function pointers and variables, bypass security mechanisms, and in the worst case scenario, you can load your own code and then execute it directly, which can be pretty crazy. So during this presentation, I'm going to go over I would like to go over 2 types of buffer overflows. I think we'll only have time to go over the stack ones based on my demo from earlier. But if we have time, we'll also cover the heap buffer overflows. And for this lingo right here, just the stack and the heap, they're both memory structures that your operating system uses. Every program has, I should say, every thread has its own stack, and every program also shares the same heap. So these are all just memory locations associated with a process that's running on your computer. Taking a more visual approach to this is how the memory of a stack looks like. The important part here is that stack memory, I'm not sure you can see my mouse here, but it grows towards the lower addresses. So we have HG return address and then some other data structures right here. Now what happens if we overflow H? Let's see what happens. Well, suddenly we've corrupted the variable G on the stack. So if there were any logic flows that, let's say, G represents an authentication variable, suddenly you've overflowed that. Now your authentication is no longer 0, but it is greater than 0. And when your program checks, it says, oh, this value is enabled, so now you're authenticated. And you might have just bypassed a security feature like that. Now, taking a step further, overwriting the return address, instead of returning to a caller, this function's caller, we could just redirect execution flow to some other program function like evil right here. And the heap structure is a bit more different. It varies per implementation, so I'm not going to show that unless we have time later on in here. So for all those of you who know me, I'm mostly a demo guy. I'm not so much of a PowerPoint person. And I like to show these sort of attacks and countermeasures happening in the real deal. It actually happened in practice. And I think that's also pretty fun because it reminds people of CTFs. So let's see if I'm going to swap my screen here to my Kali Linux instance. So I temporarily stop presenting. Let's present a different window right here. I have a virtual machine going on here. And we are presenting a screen. Does everyone see a Kali Linux login? I'll take that as a yes.
Sure.
Yeah.
Awesome, Julian. All right. So I prepared, I think, 7 examples, maybe more than that. But I'm going to see how many we can get through right here to make everything as clear as possible. So we're going to start out with a basic program here. And this is a vulnerable program, and I also have my operating system configured to be vulnerable. So here's a C program for you. It's just a simple app. It has a 64-character buffer, and we're going to corrupt this buffer of memory to change the modified variable. And if we change the modified variable, if it's greater than 0, it will say you have changed the modified variable. And in practice, you might think, instead of having this variable called modified, we could say authenticated, and then if you change it, you would have bypassed a security mechanism through a buffer overflow. So let's see if we can just do that by just running the app. So let's run stack 0 and let's just spam it with a bunch of A's, right? It's just, and boom, we've changed the modified variable, but we've also crashed the application. And in C and C++ programs, whenever you crash them, your operating system will scream at you saying segmentation fault. And it doesn't take a genius to just run this program here and just throw a bunch of stuff at it. It's very simple. And this goes back to my point of why denial of service attacks are so commonly associated with buffer overflow attacks. It's just simple things like this. So you might think, okay, well, how do I go and fix this? Well, if we go ahead and take a look at the gets function, because this is what actually reads our input. The first thing is never use this function. And fortunately, when you compile a program like this, well, for those of you who don't know, compilation is when you take some source code and then you turn it into something that's understandable by your computer when you run it. And the compiler will scream at you and tell you to never use this function. And the reason why you don't want to use this is there are no bounds checking when you read input. So I was able to read more than 64 A's right here and eventually crash the program. Now, if we take a look at the secure version, all it took was changing one line right here. So rather than running gets, we now have the fgets. And if this is kind of a bunch of gobbledygook, we can take a look at the Linux man pages to understand more what this is doing. So we have an input. We can think of a file, so it doesn't. Standard input is when you write console in, and then you have a size, the amount of data that you want to write, and then the buffer in memory that you're writing to. So if we go ahead and overwrite and just only write the size of this buffer, that's 64 characters, we're never going to write more than that, and the program is never going to crash, nor are we going to change the modified variable. So let's just see how that looks like in action. So stack 0 secure, and then spam it with A's. Make sure we have a similar amount, and it says try again, and that's because we never touched the modified variable, and we didn't even get a segmentation fault. We didn't even crash. So it's really just as simple as this. And when you're looking in your source code, always check for dangerous function calls like gets, especially ones that don't require bounds checking, and even also just being aware of the size of the data that you're moving in. So if I had maybe another buffer here that was like 128 characters, and I take the size of the wrong buffer instead, then I still have a buffer overflow, right? So that's sort of how you can detect these stack buffer overflows in when you're reading your source code.
So Brian,
and if you're hunting for, yes.
Sorry, I echo that. Is there a list somewhere of all these dangerous functions that you shouldn't use, depending on the programming language that you're using?
Yes,
I don't want to put you on the spot.
It
just kind of popped in my head.
Yeah, it's a good question, Julian. So, like I said, with when you try to compile something, your compiler usually does a really good job at knowing which functions are dangerous. Of course, this is an obvious one, gets, right? But there are also less obvious ones where even though you're using a secure mechanism to copy the data over, you might have other variables around here that will still result in the buffer overflow. But yeah, in short, your compiler should handle most of them. Other than that, I would have to say use a static code analyzer, or I'd have to look up something off the top of my head.
Peer review and static code analyzer. Yeah, no, definitely. Thank you.
Yep. All right. So moving forward, let's move on to, if we saw that overwriting a variable was bad, well, how can we control the value that we overwrite? And the answer is yes. We can, threat actors can, when they develop exploits, can control exactly what value gets modified. So I've prepared a little exploit here. So I'm just going to go ahead and run it. And this is just going to send a bunch of A's and just enough so that once we overflow this modified variable, it will be exactly this value here. And you might say, hey, the last values of this buffer are just these four right here. It's DCBA. And that's because hex 61 is lowercase a in ASCII. Hex 62 is lowercase b in ASCII, and so on and so forth. You can go to man ASCII if you want to really take a look at this in detail. So 61 is an A, and then 62 is a B, and so on and so forth, right? Now here it's reversed, and that's because of little endian. Little endian is a technical term for saying, hey, I'm going to read the A first, and then the B, and then the C, and then the D, and then shift over 8 more bytes, and then read backwards again, shift 8 more bytes, and then read it again. And that's because I'm running this on a 64-bit machine. But anyways, that was a quick example for just to demonstrate that you can go ahead and modify these values. And now let's do something a bit more interesting, something a bit more dangerous other than just changing a structure here. What if we change control flow, like a function pointer? So here's another example, and we're going to overflow this buffer into the lower memory address regions, overwrite this function pointer, and make it point to win. And then we're going to use this, like originally this code would not have been called, but suddenly if we go ahead and point the function pointer to it and invoke it right here with the brackets operator, we'll be calling that and executing that, making the program say code flow successfully changed. So let's see what we have here. Let's go ahead and see what we got with this. So I'm just going to go and I'm going to throw this in the debugger for you guys, because I think it would be cool to examine what happens in action. And this is also a good opportunity to show a countermeasure that your compiler introduces to thwart such attacks. So in this case, I'm running this. I'm going to be hacking this executable here, stack 3 with no PIE. So PIE stands for position independent executable. And just to show you, we can see it says no PIE. I'll get into more on what that is after we hack this app. So let's go Python 3, exploit, debug. So go ahead and debug this. And for those of you who are a bit familiar with debugging on or debuggers in general. I'm running GDB to debug this on Linux. GDB does not look like this out of the box. I'm using a special plugin on GDB called GEF, which stands for GDB Enhanced Features. I highly recommend you look it up, even if you're not doing exploit development, even if you're just writing regular C++ code. It has a lot of good features. But I've scripted this so we can continue running. And oh, sorry, I thought I put a breakpoint on this, but I did not. Sorry, let me quickly turn this off right here. We're doing some live debugging on a live stream, but that's what we do, right? We'll continue. Cool. So basically, I just ran this program, sent it a bunch of input. Notice that the way how the input is sent, it says 414141, and then it gives you like a null byte and a carriage return. Because these were are non-printable ASCII characters, that's why this whole input is that's why it shows it to us this way. But the point here is we want to show us taking a control over the function pointer. And if we check here, we can take a look at what the win function is. So if I print win into the debugger, this is the memory address of win. And now if I print the value of the function pointer, it's the same thing. So we've overwritten it. But how does that actually look like in memory? Well, we know that our buffer is 64 bytes. And if we end on a 64-bit 64-bit platform, you can take a look at the top of the stack denoted by the RSP register. So let's just take a look at that quickly. So XXG RSP. So as we see all these 41s, we can, this address here, it's clear that this is buffer. Buffer points to this memory address here, which holds all these A's. And if we can verify that by doing, I think, XXG buffer. So yeah, we verified that it is indeed the same thing right here. Now, moving forward, we know it's 64 because we can count these, but eventually the adjacent memory structure is the function pointer. And that is how we wrote that to memory here. Again, this goes back to the little endian, that little endian subject, a little endian idea that I represented in a previous example, where here we have 0, where is it? 114000A right here. So basically this here was sent in reverse order so that it can get interpreted like this by your computer. And of course, if we continue execution, we can set a breakpoint on win, continue, and then we can see that our function pointer was invoked and our code flow was successfully changed, which is pretty neat. All right, so now that we've understood how to take control over buffer overflows, let's see what the compiler does for us and how this protects us in practice from such attacks. So here, I just have stack3 right here. And we can see that has PIE enabled. So if we take a look at, if we go ahead and reverse engineer this binary here, I'm just, the tool I'm using here is Radare 2. I don't worry too much. I just want to show you a value right here. And we can see that it's, we can see that its function address is absolute. It's static. It never changes because on this one, PIE was disabled. And when we saw it in the debugger earlier, I guess I closed the debugger window, but we do remember that we were able to predict this address. Now, in a position-independent executable, that's not quite the case. if we take a look at the more hardened binary, which fortunately your compiler introduces by default, we'll notice it's different. And this here is really just an offset from the base address at which the executable is loaded at. So how about we go examine this and see how this works in practice. So I'm going to modify my exploit right here. So instead of executing the vulnerable one, we'll execute the one that has PIE enabled. And there is another thing I want to do right here. I need to set disable randomization on, because when I show it to you in the debugger, debuggers will disable address randomization by default. So when you put breakpoints like, I don't know, 0x dead beef, the address that you're trying to break on will never change. So you can get the same reproducible results every time you run your app. But to show this concept, we need to enable the randomization. Disable randomization on. I think it should be off, right? Because two negatives is a positive. So if you have disable and then off, that basically means enable. It's confusing why they do it that way, but
quick question, Brian. Big Endian. What architecture uses Big Endian? Does the M1 chip on Apple use it? Do you know?
Oh,
that's risk based, right?
I wish I could answer that question. If someone in the chat knows.
I was kind of Googling. I know the mainframes uses Big Endian, but I thought the risk platform used it. I
do know that when you send data over the network, it does get sent over as Big Endian.
Thanks, Naomi.
So that's like a network byte order, but that's more of a different context, more so than a chip.
Yeah,
Naomi might know.
The problem is the Apple M1. The problem is more on the instruction sets are not compatible with x86. And that's why a lot of people don't like the M1 chip when they're doing development.
Especially exploit development, right?
Yeah.
So, all right. So let's take a look here. It's the same source code, so I don't have to change the other breakpoint. And we'll go ahead and run this. So let's give it a same run. Go continue. And we crashed. So even though we redirected our program's instruction to the same function that was supposed to be the win function in the non-PIE one, we crashed. So if we take a look at win, we'll see it's at a different offset right here. So here's another thing. This here still isn't random because I goofed. So kind of ignore what I did right there. And I goofed because ASLR, address space layout randomization, is another countermeasure imposed by our operating system that randomizes the base addresses. So because I have that off, that value there was predictable, which is why I had it right here in my little exploit script. So we're just going to disable, we're going to enable address space layout randomization, so we can witness the non-predictableness in the win function. So pwin. So this time we get this, which is definitely different. We'll take note of it right here, and we'll quit out of it. Oops. And then we'll run it again, and then print win, and it's different again. So 2Ds, 7A. So every time you run, they're different. So that's ASLR and PIE in action. If we want to take a closer look at a PIE, what's interesting is for those of you who paid really, really close attention for the short amount of time that I showed the offsets, we'll notice that the win function there's just this offset right here. So if I say something like, we'll do some math. So basically by subtracting the win offset from the absolute position of win, we actually get the base address at which the executable is loaded at. And once you know the base address, then you can compute any other function that's in here, independent of PIE or ASLR. So if I want to predict, because I know the base address now, I could go ahead and predict what the value of main is. So watch this. If I go and let's go px, we'll take the base address, which is this guy right here. And then we'll add the offset for main, which is this. We'll get a value. And then if we print main, it's the exact same thing. And that's kind of an example to this to show a bit more in depth how that these here are exactly offsets representing functions in your binary. So yeah, that's PIE for you. And that's kind of how it thwarts these thwarts the exploitation of certain buffer overflows. And now you can still bypass PIE, but if you want to see that, I have more resources there. All right, let's move on. Where we are? 5 minutes. We got this. So let's move on to the next example. So this example, we noticed that there is no function pointer this time, but instead we're just going to be overwriting a return address. So just to show that this works, we'll go and run the exploit, and then boom, the code flow was successfully changed. And that's because we did a precision strike with just the right amount of A's, and then hit the return address. So when we return to win rather than exiting the binary altogether. And we're going to take this a step further and try to get remote code execution and establish a reverse shell on this vulnerable app. So the only difference between this program here and the previous one is that there is no win function anymore, because we're going to be overflowing this buffer and then putting a bunch of shellcode onto the stack beyond the return address. And the shellcode that we're going to use is one that was generated from Metasploit's MSF Venom, which is going to get executed and call back to our netcat listener, allowing us to execute arbitrary commands on the operating system. So I'm going to show how this works in GDB, just so you can see the shellcode executing in action. And if this goes wrong, it might make me look really bad, or it might make me look really good. We'll see if the demo gods are with me. So I mean, the demo gods are normally on my side, right? So we're gonna chuck this payload at it, and I think we set it. We'll disassemble main. Actually, wait. The demo gods would not be on my side because I forgot to disable ASLR, because that would have got me. So let's disable ASLR. And now let's give this a shot. Now disassemble main. Make sure that. So I had to set disable randomization off right here, but we'll see if it still works. So I'm going to break on the return address right here. Go continue. And then boom, we've hit our return address. And then this here is some shellcode. So we can just step into it. We can see the shellcode execute in action. And because our buffer was placed on the stack, again, RSP is the top of the stack, it overflowed. And then we can also see the bin sh right here, which is the command for invoking a shell. So we can keep stepping with this, and it crashed. And I think that's because I forgot to set disable randomization off right here. Let's try it again. And hopefully it works. So we'll continue. And this crashed right here.
Why is my computer acting weird? I think you got a reverse shell on my computer instead of yours. What you do?
Okay, I think it. So we're almost running out of time here. I just wanted to show something cool. So we're gonna get this to work. I believe. I think we all believe. And let's run it without GDB. Hey, what's this? What's this? Sorry, I'm getting real excited. I'm executing commands. I'm not going to go into the technical details for why that worked. I did a bunch of research before this presentation just to show play with some offsets. And basically, the places where we return, these are all stack addresses, and they change because in GDB you have a different environment, and when your environment changes, the offset of your stack changes as well. So basically, I just went ahead and overflowed the stack with 72 bytes of A, and then put the return address. And the return address is going to point to the next 8 bytes that are after this thing here in the overflow, and then it'll redirect execution flow to our buffer. And yes, I think so. Now that we know that we can get remote code execution here. There is another countermeasure I want to show you guys in these 2 minutes, and that is the non-executable stack. So if we take a look at how we compiled this binary, that's right. So Nicola says NXDEP. That is correct. So in Linux, by default, the stack is non-executable, and it also introduces PIE. So we're just going to try hacking stack 5 in debug mode. We're going to try this thing again, try using the return address for the GDB environment again. Test our luck, and let's use the one for the non-executable stack and see why this doesn't work. So let's go in debug GDB. And I think I know why it wasn't working before, but all right, so let's go continue. Actually, before continuing, we'll disassemble main. Make sure we set a breakpoint on the return address. Notice that because PIE was enabled, like this, this was no longer predictable. Well, it kind of is because I'm running GDB, but it's different. So let's break on this, continue, and then boom. So let's return into some shellcode. Of course, the shellcode is corrupt, but we're gonna go step inside. So as soon as we return into our shellcode on the stack, and then we still a single step. So we're still good. And if we single step again, we're just executing something that's simple, right? And then boom, we crash. So this is the non-executable stack security feature that was happening. And I think if we take a look, check sec on stack 5, we'll notice that the stack is non-executable because we're trying to execute shellcode on the stack. The last countermeasure I want to show before we kind of wrap this up is the stack canary. And as we've seen, on GCC, the compiler by default does not have this stack canary. So you have to enable it yourself. You have to be explicit about it. Actually, I have compiler right here. So all you have to do is just add the stack protector flag. You can read more on depth for that by looking at the GCC man page. Like F stack protector. Yeah, so you can have like various configurations for your stack protector. The reason why I believe this is not enabled by default is it has performance implications. So as we've seen, we've overwritten the return address. But what a stack canary is it's positioned right before the return address. So if you overwrite that, the binary will make a check to see if that was actually modified. If it was, it's going to detect stack smashing and abort, preventing successful exploitation. So how about we very quickly, go test that right now. So we'll go stack 5 hardened. We'll check sec on stack 5 hardened. And we have the canary found. So let's go and try to hack that. So let's run this GDB debug GDB. And then disassemble main, make sure we get the right breakpoint. And we've seen that, hey, now we have this new function right here before the return address. And this is where the stack canary, this function here checks for the stack canary being overwritten. So if we go, set a breakpoint here on the return address and then go continue, we did not even hit our return address. We didn't even return. So if we do a backtrace, we'll notice that from main, we ended up in stack check fail, eventually aborting the program. And some of you who might have developed C++ apps and seen this error message, well, now you know why it happens. Stack smashing detected. If we try to continue, the program is terminated and exploitation is unsuccessful. So those are some countermeasures. What the last thing was that I wanted to show was address space layout randomization, which is an operating system countermeasure. So we'll just go ahead. We'll keep this disabled just to show the program, the reverse shell working in action. So I'm not gonna throw in GDB because that kind of broke the environment or broke the exploit. Make sure we have the non-GDB environment return address. And thank you for attending, Evan. I'm still running the wrong executable. So no countermeasures. So that works when we have ASLR disabled on our operating system. ID, we get code execution. And we're going to try again with ASLR enabled. So we're going to enable it like this. So it's notice that we're tweaking the kernel. So operating system change. And then when we try running this, we just get a segmentation fault because I wasn't able to predict the base address at which the stack was loaded, because before I was just using a predictable value right here on the stack. So this clearly changes on every run. If you're interested in bypassing that, I have more resources for that, but that's it for my demo right here. I'm going to go bring it back to the PowerPoint slides. Let's see, stop presenting. Present now, window, PowerPoint.
So I'm sure a lot of you could follow along. I know that I got lost at a few spots in there. It's really awesome to see these things. It makes me want to take some online courses and learn more. There's just so much things to learn. It's exciting. It's fun. Well, thank you, Brian.
Yeah,
Very appreciated.
Great
How
stuff.
close were some of those exploits that you did to the OSCP buffer overflow? Because I passed my OSCP, but I basically just memorized the steps. I understood a little bit about what was going on in the background, but I think the reverse shell one was very close to what you would find on OSCP. Is that right?
It was, yes. I was kind of cheating though, because in OSCP you're basically doing a stack buffer overflow on a non-protected system, just like I was doing here. But the main difference is I believe they have ASLR enabled. So instead of hard coding a return address that you can return to, you have a jump. I think you have a jump RSP or jump ESP gadget. So because the register is always the same, no matter what ASLR is, because the register is like a variable, right? You can just jump right there. And I think in OSCP, they even have multi-stage shellcode. So maybe your shellcode wasn't quite loaded at the RSP offset. You can jump to shellcode that will increment or decrement the RSP register. And then once you finish pointing RSP to your shellcode, then you jump to your actual shellcode, which would be stage 2.
Right. Yeah, I remember that. That was a few years ago. It's too bad Evans is not here. Evans just passed his OSCE, which is all about exploit development. So it would have been interesting to have his take on it. So yeah, so thank you, Brian. I think there's a few slides there. We can share the slide deck. We'll share the presentation, the recorded presentation, and I'll put in all the links of the stuff we spoke about. So one more thing I'd like to get out of the way, and I think Jason's going to do it. We're going to do our draw for the Glenn Clark pen test book. I'm going to link to his training course. It's too bad Glenn couldn't make it, because I really would have liked to hear him talk. I had a few chats with him. He's a very interesting person, and I see that he's trained a lot of people out there. So he wrote this book, and he was gracious enough to give it to us as a draw, and whoever wins it, he's just gonna, if you want to, how are we gonna do this? I'll drop my email address in the chat. If you are the lucky winner, please send me an email and with your address, and I'll get Glenn to email the book. So take it away, Jason.
Yeah, so what we did was we put everyone that was here, wrote down their names, and we did it old school, right? We put it in this fancy toque. It's a fancy New Orleans Pelicans toque. All the names are in there. So moment of truth. You guys see that? Robert McCarthy?
Robert McCarthy, there he is. All right, Robert, you can unmute if you want to. If you don't want to, just feel free to send me an email address or reach out on LinkedIn. Oh, you have a copy already.
All right, round 2. Let's go. Kevin Roy.
Kevin.
Kevin.
He's still here. Yeah, he is.
Yes. Yep.
Yeah, Kevin's been.
All right, boys.
Pretty popular cert, I guess.
Here we go. Number 3.
Did you take the exam, Kevin? Oh.
Oh.
Naomi.
Oh, she doesn't have it perfect.
Yes.
Oh, awesome, Kevin. It's great, OSCP.
Yeah, Kevin, you gotta. I'm on that journey too, so gotta let me know how you find it. It's be interesting to see how much lab time you got there. I went for the full 90 days just because I like to have that extra practice.
I found 9 days was not nearly enough.
Oh, okay.
Though again, my situation was a bit different. I jumped into doing OSCP from a software engineering background purely.
Okay.
So when it came to like system administration, I had some experience there, but it was like when you go and actually hack systems, it's a completely different game. It's very different.
Perfect. So, Brian, do you want to switch to the last slide? Oh, actually, we see the presenter view there, but it doesn't matter.
Oh, you see the... Oh, that's not the... Oh,
it's fine. I just want to thank everybody for joining. I'm just going to stop the recording. We can stay on. I can chat cybersecurity all week if you want to. I'm just going to stop the recording so that everybody who's joining us at a later time, thank you for watching this, and thank you everybody for participating today.
Yeah, thank you.